Thermodynamics is a branch of physics and engineering that deals with the study of heat, energy, and work, and their interactions within systems. It provides a framework for understanding and analyzing the behavior of matter and energy in various physical processes. Here are some key concepts and principles in thermodynamics: system and surroundings. In thermodynamics, a system is a specific portion of the universe that is under investigation, while surroundings encompass everything outside the system. The system and surroundings exchange energy and matter in various ways. State variables, also known as thermodynamic properties, are characteristics of a system that describe its condition. Zeroth law of thermodynamics. If two systems are in thermal equilibrium with a third system, they are in thermal equilibrium with each other. This law allows the definition of temperature and the construction of temperature scales. First law of thermodynamics, law of conservation of energy. The first law states that energy cannot be created or destroyed, but it can change forms. In thermodynamics, it is often expressed as delta U equals Q, W, where delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. Second law of thermodynamics. The second law has several statements, including the Clausius statement and the Kelvin-Planck statement. One common formulation states that heat spontaneously flows from a hot body to a cold body, and it is impossible to create a heat engine with 100% efficiency. Entropy, S, is a measure of the disorder or randomness of a system. It increases in isolated systems over time and provides a basis for understanding the irreversibility of processes. Third law of thermodynamics. The third law states that as a system approaches absolute zero, 0 K, the entropy approaches a minimum, and the system's entropy at absolute zero is zero. Carnot cycle. The Carnot cycle is an idealized reversible cycle used as a benchmark for maximum efficiency in heat engines. It consists of isothermal and adiabatic processes and provides insight into the limits of engine efficiency. Enthalpy, H, is a thermodynamic property that combines internal energy and pressure. It is often used to analyze heat transfer at constant pressure. Phase transitions. Thermodynamics also deals with phase transitions, such as melting, boiling, and condensation, and describes the energy and entropy changes associated with these transitions. Gibbs free energy, G, is a thermodynamic potential that combines enthalpy and entropy. It is used to predict whether a reaction will occur spontaneously at constant temperature and pressure. Thermodynamic processes. Processes describe how a system changes from one state to another. Common types of processes include isothermal, constant temperature, adiabatic, no heat exchange, and isobaric, constant pressure. Thermodynamics has numerous applications in various fields, including chemistry, engineering, physics, and environmental science. It plays a crucial role in understanding the behavior of gases, phase changes, the operation of engines, and the efficiency of energy conversion processes. It provides the fundamental principles for the design and optimization of many engineering systems. The Zeroth law of thermodynamics is one of the fundamental principles of thermodynamics that establishes the concept of temperature and thermal equilibrium. It's called the Zeroth law because it was formulated after the first and second laws of thermodynamics had already been established, even though it is foundational for the development of temperature scales and our understanding of thermal equilibrium. The Zeroth law of thermodynamics can be stated as follows: if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In simpler terms, if two systems do not exchange heat when in contact with a third system, they are at the same temperature. This concept is crucial because it allows us to define and compare temperatures without referring to specific temperature scales. It provides a basis for constructing temperature scales and is essential for the measurement of temperature itself. For example, if you have 2 cups of water, and cup A is in thermal equilibrium with a third cup of water, B, and cup B is in thermal equilibrium with cup C, then according to the Zeroth law, cup A and cup C are also in thermal equilibrium, meaning they have the same temperature. This establishes a transitive relationship between temperatures and allows us to create temperature scales. In practical terms, the Zeroth law of thermodynamics underpins the development of temperature scales like the Celsius and Fahrenheit scales, and it's a fundamental concept used in various thermodynamic calculations and applications, such as determining whether two objects are at the same temperature before bringing them into thermal contact. The first law of thermodynamics, often referred to as the law of conservation of energy, is one of the fundamental principles of thermodynamics. It states that energy cannot be created or destroyed in an isolated system. Instead, it can only change forms or be transferred from one part of the system to another. Mathematically, the first law can be expressed as delta U equals Q, W, where delta U represents the change in internal energy of the system. Q represents the heat added to the system, positive when heat is added and negative when heat is lost. W represents the work done by the system on its surroundings, positive when work is done by the system and negative when work is done on the system. In words, the first law tells us that the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system. This law is a statement of the conservation of energy, emphasizing that energy is always conserved in any process. Here are some key points and implications of the first law of thermodynamics. Conservation of energy. The first law reinforces the principle that energy is conserved, and it cannot simply disappear but can change from one form to another. Heat and work. It distinguishes between the two primary modes of energy transfer into or out of a system, heat transfer, Q, and work done, W. Internal energy. The internal energy, delta U, of a system includes the kinetic and potential energy of its particles, and any change in internal energy reflects changes in the system's temperature and other microscopic properties. Thermodynamic processes. The first law is used to analyze and describe various thermodynamic processes, such as isothermal, constant temperature, and adiabatic, no heat exchange, processes. Energy conservation in heat engines. The first law is foundational in the study of heat engines, where energy is converted from thermal energy to mechanical work. It sets limits on the efficiency of heat engines. Applications. The first law has broad applications in engineering, physics, and chemistry. It is used to analyze energy transfer and conversion in various systems, including heat exchangers, refrigerators, and chemical reactions. Overall, the first law of thermodynamics is a fundamental principle that plays a central role in our understanding of energy and its transformations in physical and chemical processes. It is a cornerstone of classical thermodynamics and has practical applications in a wide range of fields. The second law of thermodynamics is a branch of physics that deals with the relationships between heat, work, energy, and the behavior of matter. The second law can be stated in several different ways, but one of the most common statements is as follows. In a closed system, natural processes tend to increase the overall entropy. Closed system. The second law applies to closed systems, which are isolated from their surroundings. They may exchange energy with the surroundings, in the form of heat or work, but not matter. Entropy. Entropy is a measure of the disorder or randomness of a system. It is a thermodynamic state function that quantifies the distribution of energy within a system. Increase in overall entropy. The second law states that in a closed system, the total entropy, i.e., the entropy of the system plus its surroundings, tends to increase over time. In simpler terms, natural processes lead to an increase in disorder within the system unless energy is input to decrease it. This concept is often summarized as entropy tends to increase. The second law has several important implications. Heat flows spontaneously from hotter objects to colder objects. It explains why engines, including heat engines like car engines and refrigerators, have limitations and cannot be 100% efficient. It predicts that certain processes are irreversible, such as mixing two substances together that spontaneously form a homogeneous mixture. One of the key consequences of the second law is the definition of a quantity called entropy change, delta S, which quantifies how the entropy of a system changes during a process. If delta S is positive for a process, it means the process increases the entropy of the system and is consistent with the second law. The second law of thermodynamics is a fundamental principle that has broad applications in science and engineering. It plays a crucial role in understanding the behavior of physical systems, heat engines, chemical reactions, and many other natural processes.